I think I have a good start because Paul told you 80% of the problems come from batteries, and I will be talking about batteries today. I have been talking about batteries in previous OpenRadioss days also, and in other conferences. And a lot of my work builds on previous year's work. So the title is Update on Battery Safety Modeling. And I will have to tell you a little bit background before I can tell you what is the update. And maybe a lot of people today have not been to our previous presentation. So I will start from some of the basics before going to what we have as of today. So I'd like to first acknowledge my team who have contributed to our research. The work that I will be talking about today is contributions from 3 of my PhD students, 2 of the current students, and 1 of the graduate students. It goes back to many years. So I just put a little history. I started working on batteries in 2010. I was just finishing my PhD. And then I joined the Impact and Crash Worthiness Lab at MIT. We published our first paper in 2010, and we got the SAE Myers Award for that. And that was just modeling a battery pack with homogenizing everything inside it with a material that we thought is like helpful, but we didn't have any idea what is the actual material property that should be used for batteries. A little bit later, we started testing the lithium-ion batteries of 2 types, cylindrical cells and pouch cells, and we published our first papers 2012 on modeling. And the modeling that we focus on is different from what other people's have been doing. We focus on a structural mechanics of batteries versus on electrochemical properties or thermal properties or like other aspects that are way more studied. So we wanted to know when the batteries are used in cars and when they get into a crash, what happens to them and at what point they will fail, and help the manufacturers to design the protective structures with that information. So we have studied batteries at different temperatures, at different states of charge, at different strain rates, from quasi-static to dynamic loading. And we started also looking into electrochemical response of batteries, how mechanical damage affects the electrochemical response, and coming up with criteria for that. The true thickness behavior was first a few years, and it was kind of the easier part. Then the bending and in-plane loading, it was way more complicated. But we could understand that a few years later. And then after we developed cell models, we went into getting the cells into battery packs and vehicle level simulations, which can be very challenging. Even with homogenized battery models, when you get to packs, you can have 500 million elements, and it's even impossible to start that kind of simulation. So we developed tools to homogenize batteries and get them into vehicle level simulations. And the most recent thing that was published, our paper in 2024, was the Sahraei failure criteria. Actually, this is where Marian and I started working together many years ago. When I first showed some of the simulations that are the basis of this failure criteria in one of the MIT meetings, and Marian said, "Do you want me to code it?" And I said, "Yeah, that would be great." And then he developed the code, and then he trained my students, and then we worked on the validation. And now we are so proud that we are able to predict short circuit in batteries in a variety of loading scenarios 4 different types of form factors with the same failure criteria, which predicts the short circuit. So my today presentation is mostly on this short circuit criteria and the most recent update on the short circuit criteria. So don't worry, I will not be explaining everything that I showed in the history. I'll leave that if you are interested to read our publications or talk later. So first of all, what I want to mention, you may have seen in literature our previous papers or papers from other authors. What is special about this model is that we have validated that in all of the different loading scenarios. So you see this work and you see all of the load cases. In all of these load cases, it's validated. This is for cylindrical cells. And then this is for pouch cells. Again, in all of these load cases, the short circuit criteria is validated. And it includes hemispherical loading, plane strain loading with rod, in-plane loading, 3-point bending, and we can predict when short circuit happens. So the way our understanding has developed over the years from 2010 to now 2025 is we looked at the smallest component in the cell, which is a layer of separator or a layer of electrode, and we try to understand what is happening at that level, and then how we can incorporate that understanding into the higher scales to the cell level, and how we can incorporate understanding at the cell level to modules and packs and vehicles. So the scales go from microns to meters. And you need to really understand what happens in the micron level to be able to explain what you see in the meter level. I explain the modeling on a sample of a cylindrical cell. Cylindrical cells usually have their electrodes wound inside, and we call it a jelly roll. And outside there is a metal shell casing. It can be aluminum or it can be a steel. We model that with 2 components. When we develop a homogenized model for the cell, we model this with 2 components. One component is the exterior shell casing, and one component is the interior jelly roll. But when we go to each of them, like the shell casing is maybe way more well understood. We use a standard material laws, like for anisotropic properties, we use heel type of material. For the failure, we use gizmo, either by quad in radius or gizmo in dyno, with typical care failure versus triaxiality for the shell casing. But when we go to the jelly roll, which is the main energy storage part, it's not only one material. We have at least 4 main components, and the main components, we have aluminum foil, we have copper foil, and on top of that we have active coatings, anode and cathode, and then we have a polymeric separator separating these 2 from each other, and these layers are just like on each other without usually any gluing to each other. So depending on what type of loading we have, the behavior can be very different. Now we want to combine all of these layers into one material, which is a homogenized material that will represent the behavior of all of these layers. So if we understand what is the structure of this representative volume element, then we can understand how we can model that. So if we have true thickness compression, what happens is that the granular material, which is porous, will start to densify, and it starts with a softer property, and usually the metals which are parallel to these layers, they will have not much deformation. Now, if you have true thickness tension, the layers will just separate from each other. So you don't have any strength in the true thickness tension. If you have in-plane tension, then the metal layers will start to contribute. So the main thing that will control that behavior will be the metal layer. And then these are very brittle foil materials that can fail very early. If you have in-plane compression, then in the beginning, the metal layers will contribute until they buckle. And then after they buckle, then those coating layers will start to contribute. Now, if you have a sliding of the layers, like the shear, in-plane shear will cause binder. The only thing that keeps the layers together is binder. If you have out-of-plane shear, the layers will just slide on top of each other unless you have friction or compression that causes friction. So what we need to do is we need to now calibrate the material property with that understanding, but from cell level testing. So we apply different type of punch loading, flat punch, hemispherical punch loading, and global loading, bending, in-plane loading to the cells. And then we try to extract the material properties from cell level testing instead of having all of the properties of all of the components and get the properties of the homogenized material. So for the true thickness, it is easy. We just calculate that from true thickness test. For the in-plane loading, we need to understand what is the buckling strength of the foil. And then once we know the buckling strength, the behavior after that is very similar to the true thickness. So it's like shifting the curve by buckling strength. And then the tensile behavior is one of the things that is harder to calibrate because you cannot just get all of these layers and apply tension. Even if you do that, you need, if you take it out of the casing, out of the electrolyte and the wounding, then the behavior will be different. So the way we have figured out to calibrate it, we do bending tests. And then because we know what is the compression part of the behavior, and then we know that we have to have equilibrium of moments, momentum equilibrium, we have to have force equilibrium. Then we extract the tensile part of the curve by writing a code that takes into account the force displacement and takes out the tensile parts, the compressive part. If we have cylindrical cells, then we need to also understand the geometry is not as simple as pouch cells. So we have to apply global loops radially and do some like analytical calculations, maybe use some virtual work method and then get the relationship between a stress and a strain from that type of radial loading. But if we just need to calculate the buckling strength, that's easier because the jelly roll is stable on itself. So we can apply the axial force and get the buckling strength for that. Now, once we have all of these tests, in the very beginning, we used to use the MAT 63, and that was good enough for predicting the true thickness crush behavior. But nowadays we use MAT honeycomb. So we calibrate the properties separate in tension and compression in 3 normal directions, and then in shear directions, in 3 shear directions. And then we have 9 curves, and this makes the basis of the quasi-static material model in room temperature for 0 state of charge for the battery. Now, I give all of these conditions because once we have different state of charge, different temperatures, and different strain rates, then we have to modify this base model. But for today, I will not go into all of that. I will just focus on the base model and the failure criteria. So now with this model, we have been able to predict the force displacement and shape of the formation in a variety of loading conditions through thickness, bending, in-plane loading in short direction, in long direction. And this is for a prismatic cell. Our results for pouch and cylindrical cells are usually much better than this, but prismatic cells are way more challenging. That was the material model. Now we want to know what is the failure and short circuit model. So if we apply our tensile loading in on the sample of all of these layers, what happens is if there is no compression between the layers, first we will have failure of the aluminum foil, which is the most brittle material. Then we will have failure of copper foil. A little bit later, aluminum foil failure is at 0.05, copper foil failure is 0.15 strain. And then at the end, we have failure of separator, which is what causes short circuit. And that is at 0.33, for example, a strain. So the strain to short circuit in this condition will be 0.33. Now, if we have compression between the layers, then the deformation can be localized. And when we have the failure of the metal current collector, then the deformation will happen locally right under there. And then the separator failure will happen very quickly upon metal corrector failure. So the failure strain in this case for short circuit will be more equal to failure strain of the metal, 0.05. So we developed this failure short circuit criteria by considering the ratio of compressive strain to tensile strain, and the compressive strain is the true thickness compression. Tensile strain is in-plane tension. And then our failure strain, which is the in-plane tensile failure criteria, is a function of this ratio. So this is how the curve looks like, and we have done a variation of changing the friction between layers, changing the thickness of layers, changing the properties, and always we get similar type of characteristic curve. And it is the failure strain in plane direction as a function of the ratio. So we have developed this for cylindrical cells and pouch cells. For cylindrical cells, it is very important to have the direction of the layers properly considered, because if you have a mesh like this, that's our cube element mesh, each of the elements will have different directions, and that will not be consistent with what we want. So again, Marian developed a tool for us to divide one part into like each row of the element has a different part, and then they have the coordinates that are aligned with the material direction. So once we have this coordinate set up, then we can use for cylindrical cell, and then for pouch cells it's very easy because the layers are aligned with the global coordinate system. So we use now the Sahraei failure calibrating each of the load cases with their ratio of compression to tension and the tensile failure at tensile strain at failure. So you can see the blue one is the 3-point bending curve. Usually the failure happens on the tensile side, that there is not much compression, so it has the highest failure strain. Then you see the rod indentation, a small hemispherical punch, and at the end you see the pure compression cases. So the way the algorithm works is for all of the elements in the jelly roll, you check what is the ratio. And then once you know what is the ratio, you check for that ratio whether it is passing the failure tensile failure strain in the in-plane direction. If it is passing, then you have short circuit. If it is not passing, you are under the curve for that ratio, then you don't have short circuit. So once we implement that, this is now the result that we validated for a pouch cell. Under all of different loading cases, you see the places that we have those red circles are the places that we identified short circuit. And for all of the cases that we had short circuit, we predict the short circuit at the right location. And the cases that you don't see a red circle are the cases that we didn't have short circuit in the test, and our model also did not predict short circuit for those cases. Now, this was a pouch cell example. This is a cylindrical cell example. Again, you see for all of the cases with red circles, we predict short circuit. The one case that we don't predict is the case that in the test also there was no short circuit. So this was the validation for cylindrical cell. We have done at least another cylindrical cell with different chemistry. The first cell was a lithium cobalt chemistry. We also tried a lithium phosphate chemistry. For both of them, we see similar result. And then Elastina also programmed the failure criteria for us. It is now included under the honeycomb material. You can, instead of giving one number, you can give a curve, and that will be the Sahraei failure curve. So you can use it also in Elastina. You need to make sure that element orientations are correct, otherwise the result will be messy, and it's not my fault or Elastina's fault. I know the manual doesn't explain it in too much detail, but yeah, the main thing for the model to work fine is that the element orientations should be aligned with the layers of the component in the cell. Now, what is the most recent updates is the base model I told you was for room temperature, for zero state of charge, and for quasi-static loading. And I have different papers that would be out of the scope of today that shows that failure strain should be dependent on the temperature, should be dependent on the strain rate, and should be dependent on SOC. So we have added these features to the main failure criteria to make it valid for when the temperature is different. You can see for batteries between -40 degree and 60 degree, the peak force is changing from 12 kilonewton to under 8 kilonewton. So really, you cannot just have one failure criteria in room temperature and use it for all these different temperatures. And these are not temperatures out of normal range. These are the normal operating temperature for batteries, because they do heat up during use, and they can be also in cold temperatures, and these are the temperatures that are acceptable for batteries. So you really need to include that temperature dependency. Then this is the validation for temperature dependency. This is validation for a state of charge. A state of charge is less of a big deal. The range of the values are a little bit less than 8 kilonewton to more than 8 kilonewton. So the extent of that is less than the temperature dependence, but still there is a variation. Again, we have papers to show how to model the SOC effect itself, but now we have added that also to the failure prediction. The strain rate effect is significant in terms of the stiffness of the material, and we have different papers to show how to deal with that. But here the focus is mostly the failure strain itself, and yeah, we have added the failure strain dependency to the model. So most of these factors, temperature and strain rate dependency, we are using similar functions as Johnson-Cook functions that are used for metals, but they could equally help us for predicting the cases for batteries as well. once we had our base failure criteria. Now I have cool videos to wake you up in the afternoon, because I also saw a lot of blast simulations from our colleagues. So I want you to consider a new part that you can use your blast simulations on that. This is a case of a battery that we have at 50% state of charge. And next, we have a battery that is now at 100% state of charge. And this is another battery at 100% state of charge. Okay, I didn't know that the sound will also play. I just wanted to have the video, but not the sound. But you can see that this is a serious thing that you don't really want that to happen to your electric car. And that's why we see very protective structures, like very thick structures around the battery packs, because manufacturers don't want any deformation to the battery area, the battery pack area, because no one wants to have these consequences. But these are in cases that all of our measures will be bypassed. And of course, fires happen in ICE vehicles, in combustion engine vehicles too. So fires are not only for EVs. I just want to remind you that fires happen for all vehicles if the crash is severe enough. But what I like to mention here on the right-hand side, you see the different physics here. The green line is the mechanical impact, which happens only over a few milliseconds. The blue line is the voltage. Now you see that drops down in few seconds. And then the orange line is the temperature that takes minutes to go up. And the maximum temperature we see here is 450 degrees because our temperature sensor is a little bit away from where the event is, like the main point of impact. But the temperature at the main location of short circuit can rise up to 800 degrees. A lot of times question that people ask me is, do you do multi-physics simulation? What I want to show in this picture is that the physics are at different time scales. So you need to understand different physics, but in sequence. You don't need to run at the same time your mechanical structural event at the same time scale that you run your electrochemical event. So you need to know what is the temperature, for example, before the crash event. So you can do a electrochemical simulation, which I don't have it today, but we do electrochemical simulations to see what is the temperature distribution on the cell. Then you can do your mechanical simulation that says where you will have short circuit. And then you can do another electrochemical simulation or blast simulation. And that will tell you what happens after short circuit when we go all the way to thermal runaway. So yes, we need multi-physics simulations, but we don't need to run them simultaneously. We can run them in sequence, and we can use the result of one stage into the next stage simulation, because the time scales of mechanical events is very different from the time scales of electrical and electrochemical and thermal events. So with that, I stop talking about cell vehicle level and effects of different things on cell properties, but feel free to reach out to me if you have projects in batteries that you'd like to work with us. At MIT, we were having the MIT Battery Consortium with membership of different OEMs. Now, the consortium at MIT ended in 2023. I left, my supervisor retired, so the lab closed, and we started the Center for Battery Safety at Temple last year, and we are planning to continue the same kind of research with membership of different OEMs, and then we do research that is commonly useful for everyone. So everyone with a membership can get the same results of the overall research that we do. We also do single projects when we want to study some special topics. So feel free to reach out, and there's a lot more to discuss on batteries. I couldn't fit everything in one presentation, and we wanted to save a little bit time. I know it's afternoon, and you want to have your evening. Thank you.